Welcome back to Calculus 3. I'm Dr. Jeff Groh. This is your final exam review and exam 4 review. We're only going to talk about 3 problems: verify Green's theorem, verify Gauss's divergence theorem, and verify Stokes's theorem. We can categorize these as follows. In Green's theorem, you have a left-hand side and a right-hand side. The left-hand side involves a single integral. The right-hand side involves a double integral. For the divergence theorem, the left-hand side is a double integral. The right-hand side is a triple integral. And for Stokes' theorem, the left-hand side is a single integral. The right-hand side is a double integral. You should be aware of how many integrals are required on each side for each of these theorems. Green's theorem takes place in R2. On the left-hand side, you have to parameterize a curve. On the right-hand side, you calculate an area integral. The divergence theorem takes place in R3. On the left-hand side, you're calculating a surface integral, so you need a surface parameterization. On the right-hand side, you're calculating a volume integral. For Stokes' theorem, on the left-hand side, you're parameterizing a boundary curve. On the right-hand side, you're calculating a surface integral. You need to work through many examples for each of these theorems. When I teach this class face-to-face, I have my students go to the board and help each other to work these problems. Here, I'll work them out, but I'd like you to think about each step in the process as though you were solving it yourself. On the first problem, we'll verify Green's theorem for x y squared dx minus y x squared dy, and the region is defined by x squared plus y squared is less than or equal to 4. I'd like you to begin by stating the formula for Green's theorem. For Green's theorem, you integrate around the boundary of the region, m dx plus n dy. You end up integrating around r, dn dx minus dm dy dA. The region is a disk of radius 2. Let's do the right-hand side first. Integrate over the disk dn dx, that's minus 2xy, and then minus dm dy, which is also 2xy. The integrand is negative 4xy. Note that this function is positive in the first and third quadrants and negative in the second and fourth quadrants. With equal symmetry, we expect to get 0. We can verify this. Given the symmetry of the region, we should use polar coordinates. Theta will go from 0 to 2 pi. R will go from 0 to 2. We have minus 4xy, that's r squared, times cosine theta, sine theta, and then the area element is r dr d theta. 2 cosine theta sine theta is sine of 2 theta. Sine of 2 theta has a period of pi. We're integrating from 0 to 2 pi. That's 2 periods. The integral gives you 0. Now, I won't expect you to evaluate this integral if you notice the symmetry first. Next, we have to integrate around the boundary. The original integral was xy squared dx minus x squared y dy. The boundary curve is parameterized by 2 cosine t to sine t. T will run from 0 to 2 pi to go all the way around. Plugging everything in, we'll have 2 times 2 squared, that's 8, cosine times sine squared, and dx is going to be another negative 2 sine dt. Minus 2 squared is 4 times another 2 is 8, cosine squared sine, and dy is going to be 2 cosine dt. We get negative we can factor a negative 16 out of the entire integral. What's left over is this cosine sine cubed plus cosine cubed sine, all times dt. You can factor a cosine sine out and have sine squared plus cosine squared, which is 1. Cosine sine is 1/2 sine of 2t, integrated from 0 to 2 pi. That gives you 0. Let's verify Green's theorem again. This time, x squared minus y dx plus y squared dy, and on the unit disk. On the right-hand side, we'll integrate on the entire disk. dn dx, it should be obvious that y squared dy integrated on a closed loop gives you 0. So does x squared dx. The only contributing term will be the minus y times dx, which should give you the area of the region. The answer had better be pi. Minus dm dy. We get 1 times the area element. Well, that gives you the area of the region. That's pi times 1 squared. And that's pi. Now let's do the left-hand side. For the left-hand side, we parameterize the region as cosine of t, sine of t. We'll integrate from 0 to 2 pi. We'll have cosine squared minus sine all times dx, which is negative sine dt, plus y squared times dy. dy is cosine dt. Distributing, we'll have minus cosine squared sine and plus sine squared cosine, and then plus sine squared dt. I think you can see that on these first two terms, if you did a substitution u equals cosine t, du would be minus sine t dt. When you integrate, you would get cosine cubed over 3. On the second term, the substitution would be u equals sine t. Du would be cosine t dt. When you integrate, you'll get sine cubed over 3. On the last term, we have to use a half angle identity. We'll have 1/2 times 1 minus the cosine of 2t times dt. Cosine of 2 pi is the same as cosine of 0. This term gives you nothing. Sine, evaluated at 2 pi and at 0, is also equal to 0. And when we integrate cosine 2t across 2 periods, we get nothing. So the answer is 1/2 times 2 pi, or just pi. In our next example, we'll integrate xy dx plus x squared y cubed dy. And we'll integrate from the origin out to the point 1, 0, and then up to the point 1, 2, and then straight back along the segment to the origin. On the right-hand side, we'll be integrating over this region the derivative of n with respect to x, that's 2x y cubed, minus the derivative of m with respect to y, and that's x. We'll set this up as a double integral, dy dx. X will go from 0 to 1. Using vertical cross sections, y goes from lower curve to upper curve. The lower curve is 0. The upper curve is y equals 2x. Integrating with respect to y, we get the integral from 0 to 1 of x y to the 4th over 2 minus xy, evaluated from 0 to 2x dx, or the integral from 0 to 1, plugging in 2x for y. 2 to the 4th is 16 over 2 is 8. We'll have x to the 5th minus 2x squared dx. Integrating, we'll have x to the 6th over 6. We can cancel and get 4/3 x to the 6th minus 2/3 x cubed, evaluated from 0 to 1. That's 4/3 minus 2/3, and the answer is 2/3. On the left-hand side, we have to break the integral up into 3 parts, on curve 1, curve 2, and curve 3. Curve 1 is parameterized as t0. Y is 0 all the way across. T will run from 0 to 1, taking us from 0 to 1, 0. We integrate from 0 to 1. Note that y is 0. And so we pick up nothing across the bottom of the curve. On curve 2, the parameterization has x equal to 1. And y will vary as t, where t runs from 0 to 2, taking us all the way up to the point 1, 2. In this case, dx is 0. X is equal to 1. Y is equal to t. We get t cubed times dy. dy is dt. This gives us t to the 4th over 4 evaluated from 0 to 2. 2 to the 4th is 16, divided by 4 is 4. 0 plus 4, we have a running total of 4 so far. We better end up with something negative on C3. There's no one way to parameterize a curve. There are easy ways and more difficult ways. I'll show you 2 ways of parameterizing this curve. One way is x goes from 1 to 0. Why not something like 1 minus t, where t goes from 0 to 1? But y goes from 2 to 0. You'll have to have something like 2 minus 2t there. That way when t is 0, you're at 2, and when t is 1, you have a y value of 0. This gives you the correct orientation. You can parameterize it the wrong way, but just negate the integral. It might be easier to parameterize minus C3 as r of t equals t 2t, where t runs from 0 to 1. In this case, in order to get the integral in C3, we'll do minus the integral from 0 to 1 with r of t plugged in here. Notice that we will get t times 2t dx is dt. X squared is t squared, y cubed is 8t cubed, and then dy is 2 dt. We'll have minus 2t cubed over 3 plus 16. We have t to the 5th, so it's going to be t to the 6th over 6, evaluated from 0 to 1. Plugging in 1, we'll have the negative of 2/3 plus 8/3. That's the negative of 10/3. The first curve gave us 0. The second curve gave us 4, and the third curve gave us negative 10/3. 4 is 12/3 minus 10/3 gives us 2/3, for which we are very happy because that checks with the other side. In our next example, we're going to integrate y squared dx plus x squared dy, and the region is going to be bounded by y equals x squared over 4, going this way, and then straight back along y equals x. We'll go out to the point intersection, which is at x equals 4. You can tell that because when you set them equal to each other, x equals 0 is not the solution we were looking for. We already have that one. So if we divide that off, you end up with x equals 4. On the right-hand side, we'll integrate over the region. dn dx is 2x minus dm dy, that's 2y, dA. Setting up the limits of integration, we'll have 2x minus 2y dy dx. We'll use vertical cross sections. X will go from 0 to 4, y goes from lower curve to upper curve. The lower curve is x squared over 4, the upper curve is x. Integrating with respect to y, we'll have 2xy minus y squared evaluated from x squared over 4 to x dx. This gives us the integral from 0 to 4 of 2x squared minus x squared minus 1/2 x cubed minus x to the 4th over 16 dx. We can distribute the negative here. Combining like terms, we'll have 1x squared here. Integrating, we have x cubed over 3 minus x to the 4th over 8 plus x to the 5th over 5 times 16, that's 50 and 30, that gives you 80, evaluated from 0 to 4. It might be easiest to evaluate this thinking of 4 as 2 squared, because the powers of 2 are something you should know. 2 squared cubed is 2 to the 6th. That's 64/3. 2 squared to the 4th is 2 to the 8th. That's 256, and we're divided by 8. 2 squared to the 5th is 1024, divided by 80. We can reduce these fractions somewhat. 8 goes into 256. Remember, 256 is 2 to the 8th, divided by 2 cubed is 2 to the 5th. 2 to the 5th is 32. 16 goes evenly into 80. 16 goes into 80 5 times. The numerator is 2 to the 10th, and we're dividing by 2 to the 4th. When you cancel, you get 2 to the 6th. That's 64. 32 factors out of everything that's left. That leaves us with 2/3 minus 1 plus 2/5. 2/3 minus 1 is negative 1/3. That gives us negative 5 and 6 is positive 1 over 15. The answer is 32/15. We'll preserve that over here until we do the left-hand side. On the left-hand side, we'll have to break the curve into two pieces, curve 1 and curve 2. For curve 1, we can find the parameterization t squared over 4, where t runs from 0 to 4. We get the integral from 0 to 4 of t squared over 4 squared times dt, dx is dt, plus t squared times dy, dy is 1/2 t dt. We'll have t to the 4th over 16 plus t cubed over 2 dt. This gives us t to the 5 over 80 plus t to the 4th over 8 evaluated from 0 to 4. Plugging in, we have 1024 over 80 plus 256 over 8. We now have to integrate along C2. Along C2, it might be best to reverse the orientation and go along the curve t, it's y equals x. If x is t, y must be t as well, where t runs from 0 to 4. We get the integral from 0 to 4 of t squared dt plus t squared dt, two of the same. This gives us a negative as well because we had to reverse the orientation. We'll have minus 2 t cubed over 3 evaluated from 0 to 4. 4 cubed is 64 times 2 is 128. We have minus 128 thirds. 8 goes into 256 32 times. 16 goes into 80 5 times. 16 goes into 1024 64 times. We have a total of 64/5 plus 32 minus 128 thirds. Factoring 32 out of this expression, we'll have 2/5 plus 1 minus 4/3. 1 minus 4/3 is negative 1/3. That gives us 6 minus 5. 6 minus 5 is 1 divided by 15. The answer is 32/15. I believe we're ready to move on to problems where we verify the divergence theorem. Let's say our vector field is 3x, xy, xz. And let's work on the unit cube. One unit on each side. The divergence theorem says that if you integrate around the boundary of some solid region, f dot n ds, that's the flux. You'll get the same thing if you integrate over the entire solid region, the divergence of f dv. Let's do the right-hand side first. On the right-hand side, we integrate over the solid region, the divergence. The divergence is 3 plus x plus another x. That's 3 plus 2x up against a volume element. We get 3 times the volume plus the sum of these x's times 2 across the region. Let's set up the limits of integration. We'll have dz, dy, dx, all going from 0 to 1. This being constant relative to x, we get this constant times the interval length. But the same can be said with respect to y. Applying the fundamental theorem of calculus, we'll have 3x plus x squared evaluated from 0 to 1. The answer is 4. We'll preserve that answer over here. For the left-hand side, we have to integrate over the surface of the cube. Unfortunately, there are 6 faces. We'll have on the bottom surface 1, and then on this side surface 2, surface 3 around the back, surface 4, right on the left side, surface 5, and then on the top, surface 6. On surface 1, the bottom, the normal vector pokes straight down. It is minus k. If we dot f with that normal, then we get minus xz. And when we evaluate that on the surface S1, all of the z's are 0. We deduce that on surface 1, the integral of f dot n ds is 0. There is no flux through the bottom boundary. On surface 2, the normal pokes straight out parallel to the x-axis. The normal is I. So f dot n on this face will be 3x, which when evaluated on surface 2, x is 1. We'll have 3. The surface element is easy to find. Surface 2 is parallel to the yz plane. Its surface element will be dy dz. So we'll be integrating over surface 2, 3 times its surface element. That's 3 times the surface area. The surface area of the face S2 is 1, so the answer there is 3. That gives us a running total so far of 3. On surface 3, the normal pokes straight over to the right in the direction of the positive y-axis. That's j. F dot n in this case is xy. At this particular face, y is equal to 1. So we're just integrating x. The surface element, since this face is parallel to the xz plane, will be dx dz. It follows then that the integral on S3 of f dot n ds will be the integral from 0 to 1, 0 to 1, x dx dz. Since there are no z's on the inner integral, we can just multiply by 1. The answer is going to be x squared over 2 evaluated from 0 to 1, or 1/2. So far we have a running total of 3.5. On S4, that's the back face. The normal is minus I. So f dot in this case will be minus 3x, but we evaluate on S4. And on S4, x is 0. So the flux on S4 is 0. Still a running total of 3.5. On S5, the normal pokes straight back, parallel to the y-axis, but in the opposite direction of j. So f dot in will be minus xy, which when we evaluate on surface 5, the y-coordinates are 0, so the flux on S5 is 0. Still a running total of 3.5. On S6, the normal points straight up, giving us k. F dot in will be xz, which when we evaluate on S6, z is equal to 1, so we just get x. The element of surface area will be, because this is parallel to the xy plane, dx dy. So we'll be integrating from 0 to 1, 0 to 1, x dx dy. There are no y's inside, so we just multiply by the interval length 1. We get x squared over 2 evaluated from 0 to 1, which is a half. We had 3 plus a half plus a half, and that gives us 4. On the next example, we are also going to verify the divergence theorem. The vector field will be xy, yz, zx. And the region will be x squared plus y squared is less than or equal to 1, 0 is less than or equal to z, is less than or equal to 1. Here we have a solid cylinder with z going between 0 and 1. To verify the right-hand side of the divergence theorem, we'll integrate the divergence of the vector field across the entire solid. The divergence will be y plus z plus x dv. Because of the symmetry of the region, there are just as many y's that are positive as y's that are negative. That means over this region, because it's symmetric through the xz plane, the first term gives you nothing. The third term also gives you nothing because there are just as many positive x's as negative x's. But all of the z's are positive, so we expect to get a positive result. To set up the limits of integration, because of the rotational symmetry around the z-axis, we should use cylindrical coordinates. Z will go from 0 to 1, R will go from 0 to 1, and theta from 0 to 2 pi. We get a 2 pi for free. Integrating with respect to z, we'll have z squared over 2 evaluated from 0 to 1, and the r left over. We'll have pi r squared over 2 evaluated from 0 to 1, and the answer is pi over 2. The boundary of the solid has 3 surfaces. On the bottom there's surface 1, on the top there's surface 2, and on the side there's surface 3. So on the left-hand side, we have to do surface integrals over all 3 parts. On surface 1, the normal is minus k because it points straight down at each point across the base. F dot in then will be minus zx, and on that surface, S1, z's are all 0. So the flux on surface 1 is 0. Let's look at surface 2. On surface 2, the normal is at each point k. So f dot n across the top will be zx, which when evaluated on surface 2, the z-coordinates on surface 2 are all 1. So we get x. We're integrating x across the top surface, but there are just as many positive x's as negative x's, and so we get nothing. On S3, we're looking at the boundary where x squared plus y squared equals 1. We'll give this a parameterization using r equals 1, theta is a variable, and z is a variable. We'll have a parameterization cosine theta, sine theta, and z. Z is free. It's not constrained by the equation x squared plus y squared equals 1. R is. R has to be 1 there. Theta is unconstrained. So t theta will be minus sine cosine 0, and tz will be 0, 0, 1. T theta cross tz will be cosine, sine, and then 0. It makes sense that the normal vectors on the edge should have a 0 component, no matter what direction you point. It's good form to evaluate f on your surface parameterization. And on our surface parameterization, x was cosine, y was sine. Y was sine, z was z. Z was z, x cosine. Now, when we calculate the dot product, we'll have cosine squared sine plus sine squared z plus 0 d theta dz. Theta goes from 0 to 2 pi, z goes from 0 to 1. On the first term, if you make substitution u equals cosine theta, du will be negative sine theta d theta. You'll end up with negative cosine cubed over 3, but cosine is the same at 2 pi and 0, which means the first term integrates and gives you 0. Of course, the last term is gone. What about the middle term? Integrating with respect to theta first, we have to use a half angle identity where sine squared is 1/2 1 minus cosine 2 theta. Cosine 2 theta integrated from 0 to 2 pi gives you nothing. Multiplying 1/2 by 2 pi, we end up with pi times the integral from 0 to 1 of z dz. That's pi z squared over 2, evaluated from 0 to 1, and that gives us pi over 2. And that makes us very happy, because that was the same thing we had on the right-hand side. I have to be a bit honest with you. On the final exam, I need to give you problems that will test your knowledge over cylindrical coordinates and also over spherical coordinates, as well as polar coordinates in the plane. So I'm not likely to give you a cube or a right circular cylinder capped off by disks on the final exam. Let's do another problem where we verify the divergence theorem. Let's suppose our vector field has components xz, yz, 2z squared, and the region R is bounded by z equals 1 minus x squared minus y squared, with z values being non-negative. In other words, we have a circle of radius 1 being capped by an elliptic paraboloid peaking at a height of 1, and the solid region inside is R. Working on the right-hand side of the divergence theorem, we integrate over R the divergence. The divergence will be z plus z plus for z dv. In other words, 6z. All across the region, the z values are positive. We're expecting a positive result. So we have 6 times the triple integral z. The right coordinates to use here are cylindrical coordinates because of the rotational symmetry around the z-axis. We'll use dz r dr d theta. Theta will go from 0 to 2 pi, r from 0 to 1, and z will go from lower surface, z equals 0, to upper surface, z equals 1 minus r squared. We get 2 pi for free. Integrating z, that's z squared over 2 evaluated from 0 to 1 minus r squared, with the r dr left over. We'll have 6 pi integral from 0 to 1, r times 1 minus r squared, squared dr. Being too lazy to do anything else, we'll FOIL this out. We'll get 1 times r minus 2r squared times r is minus r cubed, and then r to the 4th times r is plus r to the 5th. That's 6 pi times r squared over 2 minus r to the 4th over 2 plus r to the 6th over 6, evaluated from 0 to 1. We get 6 pi times 1/2 minus 1/2 plus 1/6. The answer is pi. Now, let's do the left-hand side. On the left-hand side, there are two surfaces, surface 1 and surface 2. On surface 1, the normal is minus k, because it pokes straight down at each point. F dot n across surface 1 then will be minus 2 z squared, which when evaluated on surface 1 will be 0. The flux across surface 1 then is 0. We'd better end up with pi units of flux through the surface 2. On surface 2, we'll parameterize with cylindrical coordinates, r and theta. We'll have r cosine theta, r sine theta, and then 1 minus r squared. Tr will be cosine sine minus 2r. T theta will be minus r sine, r cosine, and 0. Tr cross t theta will be 2r squared cosine, 2r squared sine, and then r. The vector field F, evaluated on the surface parameterization, will be r cosine times 1 minus r squared, that's xz, and then yz is r sine times 1 minus r squared, and then 2z, that's 2 times the quantity 1 minus r squared, squared. To calculate the flux, you take the dot product of these two and then integrate. Finding the dot product, we'll have 2 r cubed cosine squared 1 minus r squared plus 2 r cubed sine squared minus r squared plus 2r times 1 minus r squared squared. Dr d theta, where theta goes from 0 to 2 pi and r goes from 0 to 1. The first two terms have common factors except for the cosine squared and the sine squared. If you factor that out, you just end up with the integral from 0 to 2 pi, integral from 0 to 1, of 2r cubed times 1 minus r squared. And then we have the last term, 2r times 1 minus r squared, squared dr d theta. We get 2 pi for free. Often, when simplifying an expression, it pays to factor things first. We have a common factor of 2r times 1 minus r squared. In what's left over, we'll have r squared plus 1 minus r squared. This becomes just 1. So in simplifying, we'll move this 2 out. We'll have 4 pi, the integral from 0 to 1, of r minus r cubed dr. We have 4 pi, r squared over 2 minus r to the 4th over 4, evaluated from 0 to 1. That's 4 pi times a half minus a fourth, which is 4 pi times a fourth, or just pi. This makes us very happy. This is the blissful happy face, because that checks with the other side. On our next sequence of problems, we will verify Stokes' theorem. Hopefully, by the time of the exam, you'll be stoked for Stokes. Stokes' theorem says if you integrate around the boundary of a surface, f dot r, which you'll recognize as a circulation integral, you'll get the same thing if you integrate over the whole surface. The curl of f dot n ds. In our first example, we'll assume that the vector field f is minus y, z, and the surface is given by z equals the square root of 1 minus x squared minus y squared. This is a hemisphere. It has radius 1, but since we're using the principal square root, it only gives you non-negative z's. So, let's do the left-hand side first. On the left-hand side, we need to parameterize the boundary curve. The boundary curve in this case will be cosine t, sine t, followed by 0. So if I'm integrating on that boundary curve, f dot dr, I'll be integrating minus y dx plus x dy plus z dz. On this curve, z is 0. You might deduce that what's left is twice the area inside of that circle in the xy plane. The answer should be 2 pi. Let's check this the old-fashioned way just this time. We'll be integrating as t goes from 0 to 2 pi. We have minus y, y was sine, dx is minus sine dt. X was cosine, dy is cosine dt. We end up integrating from 0 to 2 pi just dt because of the Pythagorean identity. This gives us an answer of 2 pi. On the right-hand side, we need to calculate the curl of the vector field. We'll have 0, 0, and then 1 minus negative 1 is 2. We need a surface parameterization. This is a hemisphere. We should use spherical coordinates with rho equal to 1. Our parameters will be phi and theta. Theta will go from 0 to pi, but phi, which is the colatitude, goes from 0 to pi over 2. So our parameterization will be found by setting rho equal to 1. That gives us cosine theta sine phi, sine theta sine phi, cosine phi. T phi will be cosine theta cosine phi, sine theta cosine phi, and minus sine phi. T theta will be minus sine theta sine phi, cosine theta sine phi, and 0. T phi cross T theta will be cosine theta sine squared phi, sine theta sine squared phi, and then finally sine phi cosine phi. Taking the dot product with 0, 0, 2, we'll have twice sine phi cosine phi, d phi d theta. Remember, theta goes from 0 to 2 pi, and phi goes from 0 to pi over 2. Be careful about that. We get 2 pi free. An easy way to integrate this is to set u equal to sine phi, then du will be cosine phi d phi. We'll end up with 2u squared over 2, that's just u squared, sine squared phi, evaluated from 0 to pi over 2. The sine of pi over 2 is 1, the sine of 0 is 0. The answer is 2 pi. This makes us very happy because that checks with what we found on the other side. On this next example, we'll have the vector field y to the 5th, x cubed, z to the 4th, and the surface will be defined by z equals x squared plus y squared, where z goes from 0 to 1. In other words, we'll have this upward opening elliptic paraboloid capped on this curve at z equals 1. At z equals 1, that'll be a circle of radius 1. On the left-hand side, we'll parameterize that curve. That curve will have a parameterization, cosine t, sine t, with z equals 1. We'll be integrating on the boundary of the surface. That's y to the 5th dx plus x cubed dy plus z to the 4th dz. But dz is 0. We have then the integral from 0 to 2 pi, y to the 5th, that's sine to the 5th, and dx is minus sine dt, plus x cubed, that's cosine cubed, times dy, which is cosine dt. This simplifies as the integral from 0 to 2 pi of minus sine to the 6th plus cosine to the 4th, all times dt. We need to apply our half angle identities here. Sine squared is 1/2 1 minus cosine 2t, and cosine squared is 1/2 1 plus cosine 2t. We'll have the integral from 0 to 2 pi of minus 1 minus cosine 2t over 2 cubed plus 1 plus cosine 2t over 2 squared, all times dt. This gives us the integral from 0 to 2 pi. We have minus 1/8, and then when we cube, we'll have 1 minus 3 cosine 2t plus 3 cosine squared 2t minus cosine cubed 2t, and then plus 1/4 1 plus 2 cosine 2t plus cosine squared 2t, all times dt. You can see that some of these terms are 0 right away. Odd powers of cosine integrated over an entire period will yield nothing. We'll have minus 1/8 and then minus 3/8, and then we have to apply a half angle identity again, 1/2 1 plus cosine 4t, which of course integrates to 0, plus 1/4 plus 1/4 times, again, 1/2, 1 plus cosine 4t, all times dt. Cosine 4t, of course, integrates to nothing. All that's left is constant, so we end up with 2 pi times whatever that constant is. Let's see what we have. We have minus 1/8 minus 3/16 plus 1/4 plus 1/8. The 1/8 go away. 1/4 is 4/16 minus 3/16 is 1/16 times 2. The answer is pi over 8. Let's preserve that over here. Pi over 8. On the right-hand side, let's calculate the curl of the vector field. We'll have 0, 0, and then 3x squared minus 5y to the 4th. We need a surface parameterization. The surface has rotational symmetry around the z-axis, so we'll use cylindrical coordinates, r and theta. X will be r cosine theta, y will be r sine theta, and then z will be r squared, since z was equal to x squared plus y squared. We have tr is cosine, sine, and 2r. T theta is minus r sine, r cosine, and 0. So that tr cross t theta is, in this case we get minus 2r squared cosine, minus 2r squared sine, and r. We get a positive z component. We get negatives because these vectors are pointing back in towards the origin, but up. Next, we'll evaluate the curl of the vector field on the surface parameterization. That's going to be 0, 0, 3r squared, 3x squared, that's 3r squared cosine squared, minus 5r to the 4th sine to the 4th. Setting up the surface integral, r will go from 0 to 1 and theta from 0 to 2 pi. We'll take the dot product. We'll end up with the integrand being 3r cubed cosine squared minus 5r to the 5th sine to the 4th dr d theta, multiplying r times each of those. Integrating straight up with respect to r, we'll have 3 r to the 4th over 4. Cosine squared is 1/2 1 plus cosine 2 theta minus 5r to the 6th over 6th, and then sine to the 4th. You can see that the integral of cosine 2 theta from 0 to 2 pi will give you nothing. So far, we'll have 3/8 minus 5/6. Now the sine to the 4th, that's 1 minus cosine 2 theta over 2 quantity squared. The first term is going to be, let's just leave it, 3/8 minus 2 squared is 4. We'll have 5/24. 1 minus 2 cosine 2 theta plus cosine squared 2 theta, all times d theta. Of course, the integral of cosine 2 theta from 0 to 2 pi gives you 0. We have then the integral from 0 to 2 pi, 3/8 minus 5/24, 1 plus, we need to use a half angle identity again, 1/2 times 1 plus cosine 4 theta d theta. Of course, the integral of cosine 4 theta is 0. The only thing that's left are constants, so we get 2 pi times whatever that constant is. It'll be 3/8 minus 5/24 times 3/2. That's 2 pi times 6/16 minus 5/16. We end up with 6 minus 5 is 1 times pi over 8. And that makes us exceedingly happy.